Okay, everybody, this is going to be our class notes for section 12.1 and 12.2 of our text. I wanted to start off with talking about a chemical equation. So get to the beginning of your 12.1 notes, and at the bottom of that page, you're going to see an analysis of this equation. And you've probably already filled this in, but I want to spend some time here because in order to really understand stoichiometry, we have to understand what a chemical equation is, right? So if I look at this chemical equation, I've got nitrogen gas and 3 hydrogen gas will produce 2, this is ammonia gas, okay? Now, we know that we balance this with coefficients in order to make the total number of nitrogen atoms on each side the same and the total number of hydrogen atoms on each side the same. But again, how can we interpret this? There's lots of ways, okay? First off, nitrogen is diatomic. So this, if I wanted to draw that, this could be a nitrogen molecule, okay? Hydrogen is diatomic, and there's 3 of them, so I could draw 3 hydrogen molecules, okay? So 2 atoms bonded to each other, there's diatomic. Now what happens is these are going to split apart from themselves, and we're going to end up with NH3. So a nitrogen with 3 hydrogens attached to it. But we're going to get 2 of them because otherwise I would have deleted some atoms. Okay? So quite literally, I could think of this as molecules. 1 nitrogen molecule reacts with 3 hydrogen molecules to create 2 molecules of NH3. Now that's a scale that we can't see or measure, okay? But that is one way to interpret this reaction. And so that would be the molecules line, right? 1 molecule of nitrogen and 3 molecules of hydrogen create 2 molecules of NH3, okay? Now the atoms line, which I skipped at first, if we're looking at this, there are 2 atoms of nitrogen and 6 total atoms of hydrogen. And they're going to react to form a product that still has 2 atoms of nitrogen and 6 atoms of hydrogen. Another way to look at this would be 8 atoms reacts to form 8 atoms, right? The total number of atoms has to stay the same, okay? That has to be conserved. Otherwise, we're not obeying the law of conservation of mass. Okay, so we got atoms, we've got molecules, but if we notice, if we look at the atom numbers, 2, 6, 2, 6, or 8, 8, these numbers don't match the coefficients in my equation, but the molecule numbers do. 1 molecule, 1 nitrogen, 3 molecules, 3 hydrogens, 2 molecules, 2 ammonia, okay? So the 1 that's implied right here, the 3 and the 2 can represent molecules. They don't represent atoms in this case because none of my substances are actually elements that are monatomic, okay? Okay, next, if I had something measurable to do with this reaction, I could maybe have a mole of nitrogen atoms, which is 6.02 times 10 to the 23rd of these. A mole of nitrogen molecules, excuse me. And I could have 3 moles of hydrogen, which would be 6.02 times 10 to the 23rd times 3 molecules of hydrogen. And then it would create 2 moles of NH3 because 6.02 times 10 to the 23rd of this one and 6.02 times 10 to the 23rd of that one. Because a mole is a certain number of things, I can make these represent moles. So I could have 1 mole of nitrogen and 3 moles of hydrogen reacts to form 2 moles of NH3. And then it becomes something that we can measure, okay? Because a mole is measurable, a molecule is not, okay? So these numbers, 1, 3, 2, are the moles of each substance to bring it to a measurable level. And that's why we can get mole ratios from this equation. For example, every time 1 mole of nitrogen reacts, 3 moles of hydrogen are going to react. So that's a 1-to-3 ratio of molecules, but it's also a 1-to-3 ratio of moles. Or if I have 1 mole of nitrogen reacting, it means that 2 moles of NH3 are going to be produced. So that's a 1-to-2 ratio, and that's a mole ratio. But again, it can also represent the molecules, just at a much smaller scale we can't actually measure. Okay, mass. We can look at mass. Well, we know that 1 mole of nitrogen, we look at the periodic table, nitrogen's molar mass is 14, but it's diatomic. So that means that this is 28.0 grams of nitrogen. 3 moles of hydrogen, hydrogen's molar mass is 1, but again, it's diatomic. So a mole of hydrogen would weigh 2.0 grams times 3 makes 6.0 grams of hydrogen. They're going to react to create a certain number of grams of ammonia. Now, if you know the law of conservation of mass, you know that the total mass on this side and the total mass on this side have to be the same. So 28 plus 6 is 34.0 grams of NH3. Okay? But if you wanted to do it the same way we were thinking about it over here, nitrogen is 14, 3 hydrogens is 3 more, so 14 plus 3 is 17. 17 times 2 is 34. So we know that the equation is balanced correctly. So again, we have a situation where 34 grams is turning into 34 grams. So we have conservation here. We conserve the number of atoms, we conserve the number of grams, but these numbers, 28, 6, 34, do not match those coefficients. So this is not 1 gram of nitrogen reacts with 3 grams of hydrogen, okay? So the coefficients in this equation can represent molecules, they can represent moles, they do not represent atoms, they do not represent grams. And then our final one, and this one I thought the book did a strange thing. They didn't really take it to completion. So this is where we're going to get something that I do actually want you to write down. You probably don't have it written down yet. But we get volume. Now we know that 1 mole of a gas at STP is 22.4 liters. That's molar volume. That's from chapter 10. Okay. 1 mole of nitrogen gas is 22.4 liters. So I could write 22.4 liters of nitrogen. Okay. So kind of similar to what I was doing here with the grams. 3 moles of hydrogen. Well, a mole of a gas is 22.4 liters. So 3 times that, we get 67.2 liters of hydrogen. And then those react to create 2 moles of NH3, and NH3 is also a gas. So 2 times 22.4, we get 44.8 liters of NH3. Okay. This is not conserved. Much more volume on this side of the reaction than on this side of the reaction, okay? But all of these can be reduced by dividing them by 22.4. So why did we multiply them by 22.4 in the first place? This is where I kind of separate my thinking from the book, okay? 1 liter of nitrogen will react with 3 liters of hydrogen to create 2 liters of NH3. If we can simplify that ratio, why don't we? Why don't we just use it in the simplified form, which matches the coefficients in this equation? So, star, 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 okay? These 3 things are represented by the coefficients in your balanced chemical equation, okay? For every 1 liter of nitrogen, 3 liters of hydrogen will react and 2 liters of NH3 will be produced. For every 1 mole of nitrogen, 3 moles of hydrogen will react and 2 moles of NH3 will be produced. And for every 1 molecule of nitrogen, 3 molecules of hydrogen will react to produce 2 molecules of NH3. So all 3 of these things can be represented by those coefficients, and that's going to be important because it's going to help save us some time. So turn the page. We're going to go into our 12.2 section. And we're going to start doing some calculations with this, okay? So go to the section that says class notes, particles to particles, and volume to volume calculations, okay? All right, you can write this statement if you want, or you can just pay really close attention and hopefully you'll remember it. I recommend writing. You can summarize if you need to. This is the way the book always tells you to do these problems. It says you always need to convert to moles before you use the mole ratio, but that is only necessary if you're starting with mass. It's only necessary if you're starting with mass. Now pause if you need to copy that, but I'm going to do a couple of examples to explain. So here's an example problem, okay? Again, every single stoichiometry calculation that you're going to do has to have a balanced chemical equation, or you're not going to be able to get a mole ratio to switch between substances, okay? Remember also that stoichiometry is on our molar map. You will be using both sides. Sorry, I can't really get this to focus. Let's put it down. Okay, so if I'm starting in moles and I'm trying to get to moles, there's a mole ratio, okay? Moles of one substance, A, moles of a different substance, B, you need a mole ratio. This is going to come from your balanced chemical equation. Without a mole ratio, you cannot change sides from one substance to another in a chemical reaction for stoichiometry. So here, if 34.0 liters of oxygen react, how many liters of NO2 will be produced? So first we're going to do it the book way. And the book method says always convert to moles, which you can. It's just longer, takes more time, but you could do that. So let's just start with that. 34.0 liters of oxygen. Remember, you always start with what you're given in the problem. First step is convert to moles according to the book. So 1 mole, where am I going to put 1 mole of oxygen? Well, we don't want moles to cancel. So 1 mole of oxygen goes up here. And then we remember our molar volume is 22.4 liters. So 22.4 liters of oxygen is the same as 1 mole of oxygen at STP. Just keep assuming we're in STP. I won't always write it, mostly out of laziness, but we are not moving away from STP until we get to chapter 14. Okay, so my liters cancel out. Next, you use the mole ratio. So this is the book. Get to moles, use the mole ratio. Remember, we look at our balanced chemical equation for our mole ratio. This problem is dealing with oxygen and NO2. So I don't really care about NO. It's there because it's part of the reaction, but we're not dealing with it. But in this problem, 1 mole of oxygen, since there's no number here, it's implied to be a 1, will react to form 2 moles of NO2. All right? So where do I want to put my oxygen and where do I want to put my NO2? Well, hopefully you're saying, I want to cancel oxygen. So the oxygen piece needs to be on the bottom. Again, 1 mole of oxygen. So 1 mole of O2 will react to form 2 moles of NO2. So that's going to go on the top, 2 moles of NO2. All right. But the problem is asking how many liters of NO2. So I'm not done yet. Well, I'm in moles. I'm trying to get to liters. Again, 1 mole needs to go somewhere where you're going to cancel it. So 1 mole of NO2, and we know molar volume is 22.4 liters. So moles cancel. But if you look at this, what else cancels? We have 22.4 and we have 22.4. So what was the purpose of going to moles first when the ratio of moles to liters is a constant value? There is no purpose, okay? Now, when we do this calculation, whether we decide to punch those 22.4s in or skip them, we're gonna get the answer of 68.0 liters of NO2. All right, easier method. Start with what you're given in the problem. If it's not grams, you do not have to convert to moles first, okay? If we look at our molar map, if you're starting in mass, you have to go to moles. That's the only place you can go from mass. It's not connected to anything else, okay? But if you're in particles, you can go straight to particles. If you're in volume, you can go straight to volume. If you're in moles, you can go straight to moles with the mole ratio, okay? Remember, let me go back here, that these numbers, 1, 3, 2, they can represent molecules, they can represent moles, they can represent liters, okay? Right here, if they're gases, they can represent liters. So when we do this problem and everything is gases, I can assume these are liters. 2 liters of NO will react with 1 liter of oxygen to make 2 liters of NO2. So 1 liter for every 2 liters. That's way simpler. 1 liter of oxygen will react to form 2 liters of NO2. 34 times 2 is 68. Done. 1 step instead of 3. I think most people will find that that's a lot easier and a little bit less annoying than canceling things that are constant ratios. Okay, so those are the class notes for 12.1 and 12.2. I have several videos on the Breading Chemistry channel on YouTube that go through stoichiometry problems, examples, things like that. So throughout this chapter, refer to those. I will try to put links somewhere where they're easily accessible, but if you are having trouble wrapping your brain around these problems and you're not able to come see me in person or find time to meet me some other way, like via Zoom, then you're going to have to look at those problems. The more examples you watch, the easier this will be. I highly, highly, highly recommend that you always use this, okay? You say, where am I starting? Okay, so for this problem, we're starting with 34 liters of oxygen. That's a volume. Where am I trying to go? Well, how many liters of NO2? That's also a volume, but it's a different substance. So I'm going from volume of A to volume of B. The only thing I need is the mole ratio. And that's what we did, mole ratio. We use the mole ratio in liters because it is allowed to be used in liters. It's allowed to be used in molecules, particles, okay? And it's allowed to be used for moles. And it's the same ratio all the way across. The book wants you to go molar volume, mole ratio, molar volume, but that's 3 steps instead of 1. Use this and you should be able to do every single problem in our stoichiometry calculations in this class, okay? Okay, thanks for tuning in. Sorry that was a long one, and we will see you around.